Okay. We're going to go ahead and get started. We're going to do things a bit differently today. So normally on Wednesdays, I'm going to be collecting your graded problem, and we're going to be taking the quiz, pretty much whiz bang boom, first thing. This week, we didn't get as far as I had planned, hoped, on last Friday with our numerous AV issues. And then Monday, we just didn't get as far as I'd hoped because we kind of redid some of Friday. So we didn't really actually cover some of what you needed for your graded problem. I don't know if you were aware of that or not, right? So it made your graded problem really hard, yes? Yeah.
It took a minute, yeah.
Yeah, it took a little bit. So, sorry about that. To make up for it...
Can we turn in the problem on Friday?
No. But you can turn it in at the end of class. And I want to... how many people have ever had Dave Favreau as an instructor? Okay. So he took my class, he took statics last year, and he suggested that I make note packets for students, which was awesome. And I did that, and then this year I promptly forgot.
Can I have an extra one for Trev?
No. Anyone else? Yes. Not for him. And then he stopped by my office and says, "Doing note packets this year?" I was like, "Oh, that's right. That's a thing." Forgot about that. So we are going to. Okay, fine. You can have one for Travis. So how these note packets work, I put a lot of work into these. As in, I stole problems out of the book, because what Dave said was I spend so much time in your class trying to write down the little picture that you put up there or understand the little picture that I don't really get the theory. And so hopefully these will help with that. So for our online viewing audience, I will be providing these in recitation each week, and then I'll give them to you. So this is the note packet from today. Going forward, this will cover until next Wednesday, right? Or should be. They're kind of loosey-goosey. Sometimes we don't get as far as we want. Sometimes we get further. But for now, here you can use these as a note packet. So the idea is, essentially, these are really more problem sets that we're going to work through together in class. Okay? Questions for me? All right, so my plan for today is I'll lecture for about 45 minutes, okay, over the last part of Chapter 3. We have 3 problems to do. We'll do that. And then I'm going to give you about 10 minutes to make any changes you want to your graded problem, okay? And then the last thing we'll do is we'll take the quiz. Does that sound okay? Are people all right with this change of plan?
Sure.
It's a permanent change of plan?
No. For the rest of the class that showed up on time, they know the answer to that.
Perfect.
Yeah.
Awesome, very much.
All right. So this is actually just going back to a 2D problem. So let's see if we can work this one to warm up. All right. A nuclear reactor vessel has a weight of 500,000 pounds. Determine the horizontal compressive force that the spreader bar AB, right, that's this guy right here, exerts on point A, and the force that each cable segment CA and AD exert on this point while the vessel is hoisted upward at a constant velocity. Why does it matter that it's a constant velocity? Because it makes it statics, right? So by it being a constant velocity, what does that tell us? Or let's draw our free body diagram, I guess. Here's point A. What forces are acting on point A? And how would you denote them?
Downward for point A.
Okay. And what would you name that guy?
Tension?
Yeah, so I'd probably say TAD. What else acts on point A? Yeah, the spreader bar, right? Which way does the spreader bar push on it? Ooh, I just gave it away. It pushes on it, right? Okay, so the spreader bar is exerting a force like this. Maybe I'll just call that normal at A. Or I could say normal AB maybe if you want. Yeah. Anything else? CA, right? I'm going to go AC. All right. Now, it looks like we have 3 unknowns. It's actually 6 unknowns. Why is it 6 unknowns? Excuse me? Not both sides. We don't have magnitude. What else do we not have? So the magnitude and the size of the force are the same. They're vectors. We have 3 of them. Right now I've just labeled 3 unknowns. What would the other 3 unknowns be in a vector? If we don't know their magnitudes, we also might not know their direction, right? So we can look and we say, okay, TAD, we actually do know its direction. It's straight down. We know all of these guys once we say, oh, that's 30, and we use our assumption that this is horizontal and that's vertical. So now we're back to 3 unknowns. But how many can we solve for? 2 in 2 dimensions, right? So we have to look at the problem and say, what else do we know? Can anyone identify some?
The weight.
All right, so we know the weight, but that's why constant velocity is really important, right? Because it's only when this is moving with a constant velocity that the tension in this rope is a known value. Okay, if you're accelerating, actually it could still be known, but you're going to have to calculate it. Okay, it's not just sum of the forces equals 0. So TAD, we can assume by looking at this and saying it's symmetric, that it's going to carry 250 times 10 to the 3rd pounds. And a lot of times we call that TAD, and this is going to be 250 kip, which is probably a new unit for you. A kip is just 1,000 pounds. Okay? So guys, if you come in late, just go ahead and sit down and I'll get you your stuff afterwards, okay? Sorry. Everyone see this new unit? Okay? Good with 250 kip? Yes, sir.
We're just saying 250 because it's split in half.
Yep.
The 2.
Yep, we're just taking it and putting it in half. All right, so now it looks like we just have the 2 unknowns of the magnitude, right? So what would we do next?
Set up the force equations that you want to solve.
Yep. Sum of the forces in the x direction is equal to 0. And what forces do we have acting in the x? TAC, cosine 30 degrees. Anything else?
Negative NA.
Yeah, minus NAB. And that equals 0. How about some of the forces in the y? TAC,
Sine 30.
sine 30
And then negative 250.
minus 250 kip equals 0. Before you solve it, what's your hunch? Do you think the normal at AB is going to be greater than the weight or less than? How many people think NAB is going to be greater than 250 kip? I do. How many people think NAB is going to be less than 250 kip? Come on, someone has to disagree with me. Okay, Rebecca and Max. How many people left their spines at home today? Oh, yeah, there we go. Okay.
Well, TAC cosine 30 is just bigger than TAC sine 30.
Okay.
It's a larger number, right?
I don't know. So, anyone solve it yet?
Yeah,
That's what the consensus is.
yeah, that's what I got.
I agree with those numbers. Thank you, Victoria. So, how was I able to postulate that NAB was going to be greater than my 250 kip? I'm going to tell you, it's not from the equations. It's from looking at the geometry. Okay? So when we have a problem like this, we can look at it and in the y direction, I can see, okay, I know that the only two things acting in the y direction are my 250 kip going down and the sine of 30 times TAC. Right? So if I look at TAC, I know in order for this to be in equilibrium, the vertical component of it over here, this has to be equal to the vertical downward force. So that has to be equal to 250 kip. Does that make sense? Because it's only the vertical component that's counteracting my TAD, or 250 kip down. Right? So it's only the vertical piece of this that's capable of counteracting that. Therefore, it's going to have to pull, in order to get 250 kip, if this is 30 degrees, it has a much longer vector in the horizontal. Right? So I know that, okay, this guy's going to be much longer, and therefore, in the x, to counteract this force, NAB is going to have to be bigger than 250. Thumbs up, thumbs down if you followed my kind of, all right.
Oh, the next one should be helpful. Graded problem.
For the graded problem, yeah. Not for this conceptual idea.
Not really sure. Because it's pulled out the forces up regardless.
Here, we're going to just scoot the page down, because I want to talk about this kind of intuition aspect of it. It's pretty important. So I'm going to give you another one here. Let's say we've got a point, and we have two identical forces going up like this. Okay? And we'll call this force A and force B. And we know we have 1,000 pounds, or 1 kip, acting down. So, a couple things that you can look at right away with this problem. You can say the 1,000 pounds has no component in the x direction, right? So that means that F sub A sub x has to be equal and opposite to F sub B sub x. Can you see that? For this to stay in equilibrium, for there not to be a force imbalance, the horizontal component of F sub A and the horizontal component of F sub B have to be equal and opposite to each other. You all right with that? Okay, so if that's true and these angles are the same, that tells us that the vertical pieces have to be the same, right? So that's what that is saying, is that F sub A y must equal F sub B y. Okay? Now, if we look in the x direction, what is it that holds the 1,000 pounds up? It's F sub AY and F sub BY, right? It's these vertical pieces of F sub B and F sub A, right? So these guys have to add up to 1,000 pounds, and they're equal to each other. So what are they? 500, right? Everybody all right with that?
Should F sub A sub x equal the negative of F sub B sub? Because
If
they're
you
in the
want.
opposite direction?
If you want. But if we were saying sum of the forces equals 0, right, we would say to the right is positive, and I'd say F sub AX minus F sub BX equals 0. But really then what that is saying is this.
Gotcha. Right.
Right? All right, so this is kind of an interesting idea. Now, I've drawn this with an approximate 45-degree angle, right? Let me draw it again. Actually, so if it's a 45-degree angle, what does that mean that the horizontal components of each of F sub A and F sub B are here? 500, right? They're both going to be 500. Everybody copacetic with that? All right. Now, F sub B and F sub A. If we do a similar analysis on this one as we did over here, what are we going to find that the vertical components of these guys have to be? They're going to be equal. And what are they going to have to, what's their value going to be? 500 each, right? Because it needs to stay in static equilibrium. Okay? But let's say that I made this angle it looks like I've drawn it maybe 20 degrees now. What does that do to my horizontal components? Makes them a lot bigger, right? Like how much bigger?
I'd say about 3 times. Try to like eyeball it.
Okay, but could we do some maths to figure out how much bigger? Anyone? So we know that, well, how about this? We know that the sine of 20 degrees is going to be equal to 500 over the hypotenuse, right? Everybody good with that? Or in this case, we wouldn't call it hypotenuse, we'd say F sub A. Or F sub A is equal to 500 divided by sine 20. What's F sub A going to be equal to then?
Very big number.
Yeah.
1,461.
1,461 pounds. Okay? Now, is that the horizontal piece? No, that's the magnitude of F sub A. So how do we find the magnitude of the horizontal piece? Cosine, right? So we'd say 1461 cosine 20 is going to give me F sub A in the x direction. Anyone get that value?
Couldn't you just go straight to tangent?
We don't, yeah, let me think. Yeah, you could. You'd say tangent 20 is equal to the rise 500 over the run F sub A x. Yep, you could. You could go straight to tangent. I just didn't see it. I thought, but wait a second, you don't know the horizontal point piece. That's the point. Right? Anyone get 1461 cosine 20?
1373.7.
1373.7. So Brendan's eyes are pretty good, right? He said about a third, or 3 times, right? What do you think this tells us if we keep making that angle smaller and smaller? What's that, Jake? Bigger? To what? What do you think the limit is as we go to 0? No? Let's think about this. I'm going to draw another one. Okay? Aren't you glad I gave you a note packet? Okay? I've got 1,000 pounds going down. And I have F sub A going horizontal and F sub B going horizontal. Some of the forces in the y direction. Is this possible? Thank you, Jordan. Is it possible?
Based on just that free body diagram, no.
It's not in static equilibrium. If this free body diagram, if we're going to mandate that this is a 90-degree angle and this is a 90-degree angle, this is not in static equilibrium. Okay? But all the time we see things that appear to be horizontal. Like, have you ever seen traffic lights hanging from a cable going across the street? It looks almost flat, but is it actually all the way flat? It's not, right? The traffic light hanging from the cable, even if the cable's really, really tight, it has just a slight angle, right? So this is a great way of force multiplication. If you ever have, I'll show you a real practical application of this. Say your go-kart gets stuck, right? Your go-kart gets stuck, and you're 8, and Dad doesn't get home from work for a while. And you've got a telephone pole right here, and you've got a rope. Now you're 8, and you could probably only push or pull maybe 20 pounds. You're not super strong. So you could just try and pull on this with 20 pounds, right? But think if you tied the rope to the telephone pole and tied it to your go-kart, okay? And you made it so that it was in a straight line and tight. And then you push on it with 20 pounds. Or better yet, you stand on it, little slack line action here, and you weigh 80 pounds. If it's truly horizontal, you could move mountains, right? Does this make sense? This is engineering, folks, right? Yeah.
Or you just buy a 1 gram winch.
You know what? You have to rely on your dad's students to give you free winches. Okay? Or for your dad to wire up the one that's in the shop. But anyways. Does this make sense? Right? This is smarter, not harder. Okay? This is what engineering is. My mantra for engineers is that we're highly motivated, lazy people. Okay? We work really hard to make life easier for ourselves and for the people around us. Okay? Yeah, Rebecca?
Can you show why that example works with like the angles of it?
It's this exactly. Only instead of 1,000, it's 800.
Okay.
Excuse me, 80, yeah. My kid's a little portly. Okay? Right? So it's the exact same thing, that the tension in this rope becomes hundreds of pounds then. Right? Until you can pull that out. Now, the problem is that as soon as you move it like 6 inches, it's diminishing returns. Right? Everyone see that?
Just keep retying the rope.
Okay. Yeah, so you'd have to have somebody, you'd have to get your 5-year-old brother to sit here and put a wedge underneath it, right, when you move it to 2 inches so that it doesn't just roll back when you get off the rope. Retie the rope, get back on it. Make sense? Okay? If you ever get stuck in the woods, try this. Okay? All right. How's everyone's intuition about forces doing? A little bit better than before class? I did something. Okay?
Good.
All right. So, what we didn't get to that would have been helpful for you on the problem was forces in 3D, right?
Yeah.
And summing them to 0. So it was the exact same thing as we did in 2D, but now we just have a third dimension. The trick, though, is figuring out kind of the coefficients, okay? How do we break it into x, y, and z components? Well, we do that by using I, j, and k and unit vectors. So the first thing we need to do is draw our free body diagram of this point A. Okay? So point A, I'm going to draw here. It looks like the crate, oh, man. I'm going to change the problem, and we're going to say that I want you to find the force in each cable. Wow, cable. If the crate weighs 300 pounds. Okay? So my free body diagram, my known is 300 straight down. So I could say maybe negative 300 k hat if I wanted, or I could just say 300 straight down. Then I'm going to have some TAC, some TAB, and then I'm going to do a force AD. Okay, why did I draw force AD going up and to the right?
It's like pushing.
It's pushing it, right? So we could have also put this vector over here if we wanted, right? We could put it on the lower left, but it doesn't really matter. Now, I have the three unknowns of their magnitudes, and then I would have three unknowns of direction, but I can get the direction based on our position vectors, right? So let's figure out RAC. Okay, RAC, that's going from A to C. So in the x direction, it looks like I go 2 feet. So that's 2 I hat. In the y direction, it looks like I go back 6 feet. So that's minus 6 j hat. And in the z direction, I go from 2.5 to 5.5. So up 3, it looks like, plus 3 k hat. Now, can I just take this and multiply TAC by that? No, because that changed the magnitude, right? So I need to find my unit vector. Let's see, 6 squared is 36, and 3 squared, that's 9, would be 45, and 2 squared is 4, 49. So it looks like the magnitude is 7. So the unit vector of AC is 2/7 I hat minus 6/7 j hat plus 3/7 k hat. Now, if you have your handy-dandy TI-89, which I brought mine today, I'm going to show you a few neat little things you can do. I think you can go second math and then go down to oops. Maybe that isn't the right spot. Is it in algebra? Maybe it's in trig. Nope, not in trig.
Go to apps.
I don't have right here apps. I don't do it this way. I'm going to go back here.
What are you trying to do?
The vector, the unit vector. I know you can get it in catalog. Yeah, so if you do unit V like this, and then I believe it has to be in square brackets, and do 2, -6, 3, close the square brackets, close the parentheses, it will give it to you, give you the answer of, or give you the value of the unit vector. Okay? Does that make sense? Kind of a handy little tool if you need it. All right? So I'd like you now, why don't you find the unit vector for AB on your own, and I'll give you the unit vector for AD, because I'm a good guy.
Such a sweetheart.
Okay? So find me RAB.
You know, Andy, you're like today's date. 10 out of 10.
Wow, you've been working on that one for a while, huh? Been waiting all year for that.
Oh, how did you input that into the sorry?
Type the word unit,
Right.
and then the letter B,
Right.
put parentheses, and then square brackets. And commas to separate the units.
Oh. So I think you can pull it up the way you did it.
Nope. Hold on to it.
Andy,
Yes.
can't you solve this using there are geometric angles as well?
Yeah, sure.
Okay. Instead of unit vectors, finding their direction using the angle.
Using the coordinate direction angles?
Yeah.
But to find the coordinate direction angles,
You have to do so
you
much more.
you pretty much find the unit vector.
Yeah.
It's easy to get lost.
It's
in the
kind of,
mud when you
it's
start making all
weird.
these shortcuts.
Yeah.
I did it both ways on the graded problem, got the same answer, and
Yeah.
it was
Yeah.
like an epiphany for me.
Oh, nice.
Wait a minute. That's geometry. That's how things work.
All right. Anybody find RAB?
Did not have a chance to.
R to B?
Yeah.
-2 line
Thank you.
plus 0.
I think it's -6J. Awesome. And then did you find a unit vector for that?
In the process.
Is the magnitude? Okay, so it'd be -2 over 6.5 I hat minus 6 over 6.5 J hat plus 1.5 over 6.5 K hat.
Why are you doing -6j hat when it says it's in the positive y direction?
Going from A to B, so I'd go -6. Yep. All right, so having these unit vectors doesn't really help us, except that it gives us the direction of each of these. So now when I write three equations to sum the forces, so I can say let's sum the forces in the x direction and set that equal to 0, and x is positive that way. I can say, well, does TAC have a component in the x direction? Yeah, I think it does, right? So I'm going to say TAC, and what component of TAC is in the x direction? Well, 2/7 of its magnitude. Okay, and it's positive. How about TAB? Does it have a component in the x direction? Yup. Plus TAB. And what portion of TAB goes in the x? Well, it looks like it's -2 over 6.5. Does TAD have a component in the x? No. Does the known force minus 300K? Nope. So we can just say that has to equal 0. And this is the exact same thing we were just doing, where we said, hey, in our last problem where we just had something simple, and we said, oh, look, well, the horizontal component of these two guys has to equal each other because there's nothing else in the x. Same thing here in 3 dimensions. The horizontal, or the x, the portion of TAC acting in the x has to equal the portion of TAB acting in the x. We've just quantified that with their unit vectors because we know that the overall magnitude has to lie along that line. So why don't you bust out some of the forces in the y for me? Okay. I'm going to freeze it, and I'm going to hide my answers while you write yours because I want you to do it on your own. Yeah.
Why did you draw for the sum of fx? Why did you draw the arrow pointing that way?
Yeah, because that's kind of the positive direction for x is that way. And then,
Oh, yeah.
right, because we're in x, y, z, yeah. Okay. So did you all get something that looked like this? Okay. So we can then do in the z.
Did you change that to force of the day or
F-A-D. That's how I was leaving it. I mean, you can label it however you want. That's how I chose to do it. So then we're looking in the z direction. It looks like TAC times 3/7 plus TAB times 1.5 over 6.5 plus FAD times 2.5 over 6.5. And then we could either say minus 300K or equals 300.
Attention, may I have your attention, please? This is a drill. Attention,
Are they gonna come on the intercom also?
No, I think that's it for the fire drill, so we can go back to learning. All right, so everyone kind of see this system of equations, how this works. You just multiply each of the unknown force vectors by their unit vector. So you have TAC 2/7, negative 6/7, 3/7, negative 2, negative 6, 1.5, and then 0, 6, 2.5. So I find it helpful after I've done this to say this is x, y, x, y, z, x, y, z. And then you can put it in your calculator like that and solve. Okay, so you have 3 equations, solve for x, y, and z. And Travis says he's already done this and got some answers. What'd you get, Travis?
For our x value, I have 221, and then 205, and 411. The drill
Did you
starts
say
at
225?
Yep. 205, 205.
205.
But the drill is also starting, so I was trying to quickly type it in before I ran out.
Yeah. Anyone else get something? Sounded like somebody else got those numbers?
I got basically everything except like 410, but it might be around.
Okay. Yeah. Questions on kind of this process? All right, I'd hoped to work one more, but because we lost some time with the fire drill, what I'd like to do now is I'm going to give you 10 minutes to look at your graded problem. Okay, so it's going to be a process very similar to what we just went over. And so I'm going to give you 10 minutes to brush up your graded problem. If you've already done it and you feel great about it, given this information, great. I'm still going to give... Well, how many people have no changes to make to their graded problem and are just like, I killed it?
Yeah.
Okay.
Eventually.
It killed me.
All right, so how about this then?
Quiz, then give everyone else the time to finish it.
And then that gives
Yeah.
different amounts of time, so if you finish the quiz fast with like longer to do the daily problem.
All right, I'll here's what we'll do. I will give you your quiz, and then you can turn in the quiz and the graded problem by the end of class.